This week's lesson is called Anomalies and Normalization. Normalization is a step we take between the initial design of a database and actual implementation where you create tables in a database. At this point in your design, you would have identified all of the entities you want to keep track of. These are groups or classes of things, people, places, or things that the users of your database want to keep track of. You would have identified all of the attributes of those entities. Ultimately, the attributes are going to be columns, and the entities will be the tables that contain them. So we've already identified at this point in our development what we want to keep track of. The question is, where is it going to go? That's what normalization decides for us. Where are the attributes, where these columns are going to reside ultimately in the final database design? Here's how it works. It hinges around the idea of data duplication. If you have in your initial design some sort of situation where the same piece of information gets stored in more than one place, it wastes space because really saving the same information repeated is a waste of time, it's a waste of space. And also it opens the possibility of something called a modification anomaly. There's that word. An anomaly is an unexpected and undesirable situation. And in this context, it refers to inconsistency in data resulting from modification. Modification operations being the inserts, updates, deletes that we do to create and modify and remove rows of data in our tables. And sometimes, if the same information is stored in more than one place, what might happen is if that information changes, you may change it in some places and not in others. And you'll end up having inconsistent data. If you have your phone number in 10 different places in the database and you change your phone number and you update 9 of those rows, you'll have one left over with the old phone number. And it won't be obvious to other users which piece of information is the correct one or why there is a discrepancy in the first place. And again, that's 9 places that it didn't need to be stored because it's one piece of information. So normalization is a step we take that allows us to break apart tables into smaller tables in larger number that result in less duplication of data and less possibility, sometimes zero possibility, for these modification anomalies. The basis of normalization is something called a functional dependency. I'll walk you through what that means. Functional dependency is a situation in which knowing the value of one attribute allows you to uniquely and unambiguously determine the value of another attribute. You would say A determines B. And the determines is used, we use an arrow to represent that. The value on the left is the determinant, and the value on the right is what is determined. Now, that doesn't mean that you can look at the value of A and automatically know what the value of B is going to be. What it means is that for any given value of A, there can be only one possible corresponding value of B. So if you know what A is, and assuming you have access to the information that you could look up, there's only one possible corresponding value of B, and so you can say that A determines B. Let's look at an example. Let's say birth date and social security number. It's pretty straightforward. The question is, does birth date determine social security number? In order to determine whether that is true, we have to ask ourselves, for a given value of birth date, let's just say June 12th, 1982, can you, knowing that information, uniquely and unambiguously determine the one and only possible social security number associated with that birth date? And if you think for a moment, you'll find the answer is no. Reason being, more than one person can be born on the same day, and more than one person will have more than one social security number, because those numbers are supposed to be unique to a person. And a birth date is also unique to a person. So birth date does not determine social security number. How about the reverse? If I give you a value of social security number, and assuming you have access to the relevant information, does that uniquely and unambiguously determine the one and only possible birth date associated with that SSN? And the answer there should be yes, if everybody has done their jobs correctly. Yes, Social Security number does determine birth date, because for any given value of SSN, there should be only one birth date. It's assigned to a single person, and a person has a single birth date. That's what a functional dependency means. And when you start looking at columns in your tables, attributes in your entities, you start to identify these functional dependencies, and that is what helps you in the process of normalization. I'll walk you through an example of this before I get into the PowerPoint slides, which are from the text. This example I've come up with on my own. Imagine you have a table of information. It's about entertainers. And in red, we have the unique identifier, the primary key. This is the entertainer ID. It's a numeric value. And we have non-key attributes of last name, first name, talent, address, city, state, and zip code. These are all the non-key attributes. Now, we have to ask ourselves if there are any functional dependencies between the non-key attributes in this example. And if there are, that means we are not fully normalized. In this case, what I'm talking about is third normal form. That's jumping ahead. But for the time being, looking at these values, you have to ask yourself, do any of them allow me to determine the value of any of the others? If I know someone's last name, for example, does that let me uniquely determine their talent or their city? No, not really. If I know their talent, does that allow me to determine their zip code? Probably not, because there can be more than one talented person in the same zip code. If I know their zip code, does that allow me to determine their city? Actually, yes. How about their state? As a matter of fact, yes. The way zip codes are designed to help people find mailboxes to put envelopes in, any given value of zip code, this unique number, corresponds to one post office, which belongs to a particular city in a particular state. So there is, we can say, a functional dependency is such that zip code determines city, and zip code also determines state. So in that case, the functional dependency is represented with two values in parentheses, connected by commas. Zip code determines both city and state. In other words, if I know the value of zip code, I can uniquely and unambiguously determine the corresponding values of city and state. Now, when that is the case, for example, these two entertainers both live in the same zip code, which is in Portland, Oregon, what we end up with is duplicate data. In actual practice, these values are unlikely to change, but just say for the sake of argument that the zip code 97201 was reassigned. It's no longer in Portland, Oregon. It's now across the river in Vancouver, Washington, for some reason. But okay. So if we needed to change the corresponding city and state values for zip code, what we would have to do is identify all the rows that have zip code of 97201, update their city to Vancouver, update their state to Washington. And if there were 1,000 of them, and we did 999, we would miss one, and you would find entries in the table resulting that have different values of city and state for the same zip code. That's an inconsistent situation. That's a data anomaly resulting from modification, an update anomaly. It's a bad thing. We don't want that to happen. We'd like to be able to prevent that. Also, if we have 1,000 entries for this same zip code, we're recording city and state, Portland and Oregon, or Vancouver and Washington, 1,000 times, when we don't really need to do that. So the process of normalization in this case, what it looks like is identification of the column or columns that prevent this from being fully normalized, and removal of those columns, in this case, city and state. Now, we do not remove the zip code column. We keep that in the original relation, in the original table, but we remove city and state out into their own table, in which zip code is now the primary key, the unique identifier. So we took one relatively large table and broke it apart into two smaller tables. And if you note carefully, this is in italics now, the zip code in the original table is now a foreign key column, pointing to the primary key of this new table, this new relation, in which there is only one row for zip code 97201. Currently it says city of Portland, state of Washington, or state of Oregon. If this were to change by some chance, bad example, but if it were to change, we would only need to update the values in this one row. A piece of information there, the connection between the zip code and its corresponding city and state, is only stored in one place. And now if that's updated, it's updated in one place, 100% consistent. In this case, it makes it impossible for the data modification anomaly as I described earlier to occur. Also, we're not wasting as much space. We don't have those two columns repeating for every single entertainer in the table. That's what normalization looks like essentially, or in this case, third normal form. What I'm going to go through next is a PowerPoint presentation that is taken from the Muroc text, chapter 10, how to design a database. These are excerpts from chapter 10. And we'll talk about the normal forms. These are degrees of normalization. It's measured in normal forms. Typically, these are numeric in name, first normal form, second normal form, third normal form, and so on. And they are built on each other. That is to say, for a relation to be in second normal form, it must already be in first normal form. And there's an additional criterion that must be true. So the rules of normal forms, I will step through here. We're going to talk about 7 of them in this week's lesson. First, second, third. Boyce-Codd normal form, which is one of the non-numeric names. It's a BCNF named after Edgar Boyce, I think, and Ted Codd. And it falls between third and fourth normal form. It's sort of 3.5, right? There's also fourth normal form, fifth normal form. And the last one we talk about in lecture is sixth normal form, sometimes referred to as domain key normal form, or DKNF. I am not going to go into any detail for these higher forms. I'm going to focus on the first 3. Those are the ones for which you'll be held responsible in your lab assignment. Those are the ones that show up on your quiz, with the one exception being there's a single question about fourth normal form that I'll talk about when I get to that, just to prepare you for the quiz. Now, the normal forms build upon each other. So in order for a relation to be in first normal form, there are some certain rules that must be true. In order for your table of information, this grid of rows and columns, to be in first normal form, the values at each intersection of row and column, each cell in the grid, must be scalar. They must contain only a single value. For example, if you have a column with a header that says phone number, in order for it to be in first normal form, you cannot list one phone number and then a comma and another phone number after it. That's the sort of information you would put on a paper form for human beings to read. That would make sense to a person. It does not make sense to a relational database management system or to computers in general to have comma-separated values. Database systems are not set up to interpret comma-separated values, so those values must be scalar. The second rule is that a table must not contain any repeating columns. This is something I mentioned and gave an example of in the lecture with the database design for mere mortals text in lesson 8, I think, lesson 7 possibly, in which we had a relationship between students and courses. It's a many-to-many relationship, and in order to actually represent that relationship, what we ended up doing in that case was creating a linking table or an intersection table in which one student was linked to one course. But before we came to that solution, we tried a couple of false starts. Notably, we tried at first adding, instead of a single student column to the course table, we added 24 different student columns, student 1, student 2, student 3, and so on. The idea being, if you had 20 students registering for a given course, you would list each of their corresponding IDs in separate columns in the same row. That is what I mean by repeating columns. phone 1, phone 2, phone 3, that sort of thing. In order for your data to be in first normal form, you're not allowed to have that. It might seem unintuitive. You might think, what's the big deal? Why can't I do that? You can do that if a person is looking at the data, but in order for a database system to process it consistently, all the data of a given type needs to be in the same column. It needs to be the same data type. All the phone numbers need to be listed in the same column. All the email addresses need to be listed in the same column. Otherwise, you end up having to search and mix and match and have join conditions between 2 or 3 or 4 or more columns, which is way too complicated in a situation that's already, as you know, fairly complicated in the first place. So to make a grid of information fit first normal form, to say that it is normalized to that degree, we have to fix those issues. If there are scalar values, we have to break them apart. If there are repeating columns, we need to get rid of them, integrate them together. In order for a relation to be in second normal form, it must already be in first normal form, and the additional rule is every non-key column must depend on the entire primary key. When you say the entire primary key, the implication is this might be a composite primary key consisting of 2 or more values. And in fact, that's the only situation in which second normal form comes into play at all, when you have a composite primary key. If your relation is in first normal form and its primary key, its unique identifier, is a single column, you can say it's automatically in second normal form because it's a non-issue. But if it is a composite primary key consisting of 2 or more columns, the combination of which uniquely identifies a row, then for it to be in second normal form, you cannot have any of the non-key attributes that could be determined by just part of the primary key, just one of those columns, or or some subset of the total primary key. In order for a relation to be in third normal form, it must already be in second normal form, and it must meet this additional rule, which is that every non-key column must depend only on the primary key. You cannot have what's referred to as a transitive functional dependency. Transitive property, if you remember from math class, transitive property of inequality states that if A is greater than B and if B is greater than C, we can deduce that A is greater than C, right? The same is true with functional dependencies. If value A determines value B, that is to say, for any given value of A, there's only one value of B. And if B determines C, for any given value of B, there's only one possible value of C. You can say that knowing the value of A allows you to determine C. A determines C. That's a transitive functional dependency. And if you have that situation in your table, it's a violation of third normal form. That, in fact, is the exact example I showed you earlier. The primary key of this table is entertainer ID. If I know the value of entertainer ID, say 2, that allows me to uniquely and unambiguously identify the one and only one row of data in this table that matches that. It's a unique value. It can't be left null. So if there's an entertainer ID number 2, there's only one row in there, which means for each of these columns, which are, of course, scalar columns, they can only contain a single value. So for any given value of entertainer ID, there can only be one corresponding last name. And I can look it up here. There can only be one corresponding first name, and so on for every non-key attribute in that table. Knowing the value of the primary key allows you to uniquely determine all of the other values. So A determines basically everything else. The primary key determines everything else. And if one of the non-key attributes, like zip code, determines some of the other non-key attributes, that means you have a transitive functional dependency. ID determines zip code determines city and state. That's a transitive functional dependency, and that means this relation is not in third normal form. How do we make it in third normal form? By doing this, by removing the column or columns that violate that rule, in this case, city and state. Now there's no more transitive functional dependency in the original relation. We have a second new relation here, which is also in first normal form. It's only got a single column as its primary key, which means it's already in second normal form. And since there doesn't seem to be any relationship between functional dependency of the non-key attributes here, knowing city doesn't tell you what state is, and knowing state doesn't tell you what city is, this is also in third normal form, the overall design. Those are the first three normal forms. There is a silly mnemonic device for remembering the rules of the first three normal forms. It is as follows. All of the non-key attributes must be dependent on the key, that's first normal form, the whole key, that's second normal form, and nothing but the key, that's third normal form. So help me God. I didn't make that up. Don't blame me. But yes, that is a way to remember the rules of the first three normal forms. So your lab assignment will, as you will see, will present you with a number of relations, a number of tables that are not normalized to a certain degree, and you'll be tasked with advancing those designs to actually advance them to the target normal form. I'll talk briefly about the other four normal forms listed here. Boyce-Codd normal form, as I said, it's like 3.5. Says that a non-key column can't be dependent on another non-key column. It's not a clear distinction between this and a transitive functional dependency. I'm not going to go into detail. You can read it in the text. Fourth normal form, there will be one quiz question asking you what fourth normal form is. It says that a table, of course, to be in fourth normal form, you must already be in third, and your table must not have more than one multi-valued dependency, where the primary key is a one-to-many relationship to non-key columns. In other words, a multi-valued dependency is similar to a functional dependency, but it doesn't allow you to uniquely identify a value. It allows you to narrow down the values. For example, let's say if you knew the value of state, that would not tell you the value of a city, because there are more than one city in any given state, but it would narrow down the list. If I tell you the state is Oregon, then the list of cities in that state automatically gets narrowed down. It excludes New York, Los Angeles, San Francisco. Those are in other states. So you would have this multi-valued dependency. So for your entity to be advanced to fourth normal form, those would be eliminated. Eliminating multi-valued dependencies, that's all you need to know in terms of the quiz. That's what fourth normal form does. Fifth and sixth and so on, these higher levels of normalization in practice are seldom used. They're more of an academic exercise in creating a higher and higher level of normalization that makes it more and more unlikely that you will have data modification anomalies. In practice, the process of normalization involves breaking relatively large tables consisting of large numbers of columns into smaller tables with fewer columns, but you end up with a larger number of tables. And the further you take that normalization process, the more tables you end up with, and the smaller and smaller they become in terms of the number of columns within them. At a really high level of normalization, some of your tables will have only 2 or 3 columns. And in order to actually write queries against tables in that design, you'll have to do a bunch of joins of many different tables, which makes it a little cumbersome and tedious in practice to use them. In practice, you'll find most designers will stop right around third normal form. Otherwise, it's more work. But the advantage of normalization is, as I say, over time, when data is added to your tables, when data is removed and modified, you can, if there is a vulnerability, you can get abnormal data. You can have violations of this resulting in inconsistent data. And the more you use a database, the more likely it is to occur at some point or another. It's like a leaky boat. If you have a small hole in your boat, it's not a big deal. It's not going to cause the boat to sink right away. But on a long enough timeline, you're going to end up bailing out that boat more and more. And by the same token, you're going to end up doing more and more data cleanup on a database that is vulnerable to data modification anomalies. So it's a short-sighted decision to not normalize, or to normalize to an only low degree. Now, benefits as noted, there's fewer repetitions of data, less duplication, which means you use less space. You actually end up with a more efficient design, even though you have a larger number of tables that might be slightly more difficult to write queries against, because each table has a clustered index, and each one of those is relatively small because the removal of the duplication. You end up with a relatively efficient database in terms of running queries. Here's an example of the process of normalization. We're going to be given a small grid of information, which is not normalized at all, not to any degree whatsoever. What we have here is a list of vendors, along with invoice numbers and item descriptions for those vendors. There's only 3 rows here, but what we find is that this example is not in first normal form. The reason being, we do not have scalar values in the cells. For the first row, Kaner's Publishing, the item description says Visual Basic add and SQL add and library directory. It's a comma-separated list of 3 values. That is not scalar. It's not a single value. So, and the second row, likewise, we have item description of catalogs, comma, SQL flyer. That's 2 different values of item description for the same vendor and invoice number. Now, in order to make this first normal form, one attempt, similar to what we did in that previous lesson, breaking apart a many-to-many relationship, we could try adding some repeating columns. So instead of having a column for item description, we have one for description 1, description 2, and description 3. We've broken these 3 values apart into separate columns. Looks great, right? And in the second column, we have 2. The third one doesn't get used. And then the third one, which only had a single description, we end up wasting the space for description 2 and 3. Just like that previous example, this has 2 issues. One, it's wasting space for all the rows that don't have 3 descriptions. And 2, it doesn't support an arbitrary number of descriptions. If we have a row that has 4 or 5 or more, we don't have the option of simply tacking more and more columns on to solve the problem, because each of those columns will be added to every row in the table. So repeating columns, in any case, are not allowed in first normal form, nor are non-scalar values. So what we have to do to put this in first normal form is basically create some duplication. The original row for Kaner's Publishing for invoice number 112897 now shows up 3 times with the same values for those fields, name and invoice number, but 1 row for each individual description of those 3 values that were originally separated by commas. Likewise, the second combination of Zilka design with invoice number 97522 had 2 different item descriptions. Now we have 2 rows for those 2 values, each one with a different description. And the third row is unmodified because it didn't have a violation of either of those rules. This is a start. We can say that this is in first normal form. It's not great. It doesn't really have a unique identifier yet, but it is in first normal form. Now, to make this into any kind of usable table, what we need to do is create a unique identifier. Because right now, the publisher name, the vendor name wasn't unique in the first place. We had 2 rows for the same vendor in any case. They had different invoice numbers. Maybe the unique combination of those 2 values could be a primary key. What we can do is add a couple of columns. One for the invoice ID. So for the original row in the first table, we'll have an invoice ID of 123. That first row has the same invoice ID for all 3 of these rows. And they have the same vendor name and invoice number, but there's a sequence over here. that has different numbers, 1, 2, and 3. That's what we've done, is created these two values that represent, on the one hand, the invoice ID, which was the original row in the table, and on the other hand, the sequence number, which breaks each of the item descriptions out into their own line numbers, a line item. Likewise, the second row in the original table now shows up twice with the same vendor name, invoice number, but sequence numbers 1 and 2. So what we have is a composite primary key identifier consisting of the combination of invoice ID and sequence number. It would help if they were right next to each other to make that obvious, but the combination of those two values in this table is unique. Now, is this in second normal form? Well, the question depends on whether or not the primary key is composite. And in this case, because it is composite, we have to ask ourselves, are there any non-key attributes, that's any of these, vendor name, invoice number, or description, are there any of those that are dependent on only part of the primary key, rather than the combination of both values? If I know the value of invoice ID, for example, well, let's say if I know the value of invoice sequence, say 1, does that allow me to uniquely determine the description? No, because I'm seeing different descriptions for sequence 1. Does it allow me to determine the vendor? No, I see different vendors and different invoice numbers for the same sequence number. So sequence number does not determine any of those other 3 columns. How about invoice ID? If I know the value of invoice ID, let's say I know the number is 1, does that allow me to determine the corresponding description? No, there are 3 different descriptions for invoice 1. How about vendor name? Looks like. Invoice number? Yes. Try for value 2. Does this allow me to uniquely determine the vendor name and invoice number for the same invoice ID? It looks like, yeah, because these were, we happen to know, in the original data, these were the original rows of data with their own combination of vendor name and invoice number. So I can say the value of invoice ID determines vendor name and invoice number. That is a functional dependency, dependent on only invoice ID, not the combination of the two. So this is not in second normal form. In order to advance the design to second normal form, what I have to do is identify the column or columns that break that rule, in this case, vendor name and invoice number, and remove them from the relation, put them into their own table. So what I end up with in my original table, nothing left except item description. That's the only remaining value that's dependent on the combination of these two. And in this new table, which has invoice ID as its primary key, are the corresponding vendor name and invoice number. They've been broken out into their own table without duplication, because for any given value of invoice ID, you know the one and only corresponding value of vendor name and invoice number. We don't have 3 rows for invoice ID 1 up here. We only have 1. That way, we don't have this data duplication. If the name of vendor Cater's Publishing was changed because it got bought by another company or something, in this design, we'd have to change it in 3 different places. And if we didn't get all 3 of them consistently, we'd end up with a data anomaly. In this new design, it's stored in a single column in a single row of this table. If it changes in one place. That's the value of normalization, and that's the process. Find the offending columns that prevent you from being in a given normal form, break them out into their own new table, their own new relation, remove them from the original, and now you wind up with a relation that is in second normal form. Doesn't violate any of the rules. Now, this one, I think we could probably say it's already in third normal form also, because there really is no more information. There's very few columns in the table. So unless invoice number determines vendor name or vice versa, I think we could probably say it's in third normal form. There's no transitive functional dependencies. I will not step through this actual example here. I'll just show you what it looks like, the before and after. This is an unnormalized design in which we have basically 2 tables of information with a whole bunch of columns. This is apparently it's in second normal form. If you advance that to third normal form, what you end up with is a larger number of tables, each one of which has a smaller number of columns. We have GL accounts that only has 2 columns, terms that only has 3 columns here. Advance that even further to fifth normal form, and it's broken down even further. Like I say, more and more tables, fewer and fewer columns in them. That's what the process of normalization looks like as you advance it to a higher and higher degree. Now, the last thing I'll talk about briefly is denormalization. That is the practice of intentionally violating the rules of normalization as a compromise. This is sometimes done when high levels of normalization result in complicated relationships between many tables. If you were to try to write a report off of a database with this design, the queries would have to join together 3, 4, 5 tables or more in order to get the data, which maybe you just want to have outputted to a form so people can review it. So if you intentionally denormalize your database, you add, say, a reporting table in which data from these other tables is repeated, what you end up with is data duplication, a waste of space, but one big simple table you can go to for your reports. That's what denormalization is done for. Simplicity of retrieving data. It's one of those shortcuts that has all of the same issues of an unnormalized database, all the same dangers, and it can, I promise you, I've seen it happen, can bite you by getting out of sync with the actual data. You can have data anomalies, but it's still done sometimes just as a simple compromise for simple reporting processes. Let's talk about the lab assignment based on what I've just shown you. You're given a Word document describing the questions, and you're given an Excel spreadsheet with 5 tabs. Each of these 5 has a relation, a table of information, which is not normalized, at least not to any great degree. And in the instructions for each of the 5 questions, you're told what you're tasked with doing, the normalization to which you need to advance this particular design. Generally speaking, you'll see primary keys are in red. If possible, I'd like you to continue to represent your unique identifiers with a red header. Makes it easy to read. And the non-key attributes are listed in black. Here are the 5 problems, and I'll step through them very briefly. Problem number 1, you're given a grid of information about people with their address, city, state, and phone information. You're supposed to apply first normal form to this table. That means removal of repeating data and winding up with only scalar values in the cells and no repeating columns. Here's what the problem looks like. The 1NF example, we have a unique identifier of name, address, city, state. What we have in here is some phone numbers that are separated by commas. You have multiple values in the same field. It's a non-scalar value. And if you look closely, you'll see also there's an email column here that has at least one example of multiple values separated by commas. It's not scalar. A single value is a scalar value. In order to advance this to first normal form, you need to do something like I showed you in this example here. We can't use repeating columns. What we need to do is take those non-scalar values, those compound values, break them apart, and put them each in the same column. So the descriptions are all in the same column, but you end up with some repetition of data, some duplication of the other non-key columns. So to do that here, here's the problem. Below is where your solution goes. What you can do, for example, copy this, paste it down here. If I take this row of data from Mary Johnson, I copy it, I insert that below. Now I have 2 entries for Mary Johnson. I'll keep the first phone number in entry number 1. I'll keep the second phone number in entry number 2. That breaks apart the non-scalar value of phone number. Now I have duplication, but I'm getting closer to first normal form. This one also has duplication. Paste the cells. Keep the first email address in record 1. Keep the second email address in record 2. And so on and so on. Do the same thing with this last entry because it also has 2 phone numbers. What you'll end up with is duplication, but it will be in first normal form. None of the rows, none of the columns will have non-scalar values in them, none of these cells. And we won't have repeating columns like phone 1, phone 2, and email 1, email 2, and so on. Strictly speaking, this is no longer a unique identifier. So what you're not required to do, what you could do is add a column like ID, right? Make this no longer red. And I could give this a unique value, something like that. Now I have a unique identifier in red. I have, with the exception of this last row, only scalar values in all the cells, no repeating columns. That would be in first normal form. That's basically what you're required to do for question number 1. Looking at the instructions, question number 2 will tell you you are given information about U.S. cities, a grid of information, which has, as you can see, a composite primary key. The combination of city and state is what uniquely identifies a city. You have, for example, Portland, Oregon. You have also Portland, Maine. So city on its own is not a unique identifier. You have Dallas, Texas, and Austin, Texas. State on its own is not a unique identifier. It's the combination of the two that uniquely identifies a row. As the instructions tell you, you're supposed to advance this to second normal form. And if you remember, second normal form states that none of the non-key attributes can be dependent on only part of the key. In other words, if there's any column that's dependent on only part of the primary key rather than the combination of the two values, that needs to be removed and placed into its own column. Now, things like population do seem to be unique to the combination. City area, square footage, likewise. Mayor seems to be different for each individual city. Governor, funny thing, governor is someone who rules over an entire state, not just one city. So for all of the cities in Texas, you'll have the same governor. For all the cities in Oregon, you'll have the same governor, right? That's going to be true, presumably, for every state in the union. So governor column violates second normal form because state determines governor. In order to advance this to second normal form, what you're going to have to do is remove the governor column, put it in its own table. The unique identifier of that table is going to be state. So in the original relation, governor's now gone, state will still be there. It will still be part of the composite primary key, but up here it will also be italics, a foreign key pointing to the primary key of that other new relation. One last thing you want to do with that is make sure in your new relation, since you only have state and governor, to get rid of duplicate values. You should have only one value, only one row for every unique value of state. I'll leave that for you to solve. Question 3, you'll advance this to third normal form. If you're not sure about assumptions, or if you have questions on this, on any of these individual problems, check the instructions here to see if there's any clarification. This contains invoice data, including customer and contact fields. It's already been advanced to second normal form. You can glance at this, see it doesn't contain any non-scalar values. These are all individual values in each cell. doesn't have any repeating columns, that means it's in first normal form. It's only got one column as the primary key. That means if it's in first normal form, it's automatically in second normal form as well. It's your task to advance it to third normal form. What you want to do is eliminate transitive dependencies. That is to say, are there any values in here which could be determined by the values of other non-key attributes? Taking a look at the data, we have invoice as the unique identifier. Non-key attributes include date, total, customer number, customer name, customer phone. Can you find any functional dependencies in this data that are based on other non-key attributes? I think if you pay attention, you'll see that customer number determines customer name. It also determines customer phone. And as you can see, just to verify, in records that have the same customer number, likewise, they have the same name and phone number. So customer name and phone number are the columns preventing this from being in third normal form. They need to be broken apart out into their own table in which customer number will be the unique identifier with the any possible duplicate values removed. You'll only have one value of customer number, one row for customer number 100, and so on and so on. This is directly analogous to the example I gave you for the entertainer table, where we broke out city and state and made zip code a foreign key. Exactly the same thing. That's question 3. Questions 4 and 5 are also related to third normal form, but in the case of question 4, they are not numbered. But in the fourth question, you're given a table that has not been normalized at all. And you are tasked with normalizing it up to first, and then second, and then third normal form, stepping through the same process you did for the previous 3 questions, but doing it all the way yourself. So looking at this info, you have data on entertainers and performances. You have a unique identifier of the combination of performance and entertainer. Non-key attributes include the date of the performance, the venue, the address of that venue, talent, and salary. Now you'll see some of these contain non-scalar values. This one row for performance 126 had 2 entertainers with 2 talents and 2 salaries. For clarity, question 4 will tell you in the notes, there's a clarification here that says more than one entertainer can be booked for a single performance, as we've seen, and that we can assume that salary is a standard charge for each entertainer rather than performance specific. In other words, if Bob Goldthwait has a talent of comedy and gets paid $250, we can assume that's going to be true for any corresponding performances he may have. And if Yo-Yo Ma plays cello and gets paid $5,000, you can assume that's a standard charge. So when advancing this design, you'll need to remove these non-scalar values, break them apart so that you have duplication. You'll have 2 rows for performance 126, each one with a different entertainer and their corresponding talent and salary. To advance that to second normal form, you have to look at the 2 columns that make up the primary key and find any non-key attributes that would be specific to just one of them instead of to the combination of both. The date, the venue, the address. Are any of these specific to just the entertainer or to just the performance? And lastly, when you've advanced it that far, look for transitive functional dependencies among the non-key attributes. If knowing the value of one of them allows you to determine the value of another, hint, venue determines address, you'll need to break out the offending column or columns into their own table with the corresponding unique identifier of the new primary key. Nothing new, just the same steps taken in the previous 3 questions, but doing it all the way from the beginning to end. Your final solution will go down here. For the last question, number 5, you're given student and course information with grades. It's in first normal form. It has been advanced to first normal form, but has not been further normalized, and your task is to advance it to third normal form. Again, this does have a composite primary key, the unique combination of student and course, and a series of non-key attributes. These are the columns dependent on the whole key. And your task is to advance this to third normal form such that there are no transitive functional dependencies. Depending on your interpretation of this, it can go several ways. But ultimately, for each combination of student and course, there is a corresponding grade. There is a term in this format. 2018-04 is fall term, the year of 2018. This is actually the same format used by the information system we use at the college in the database system underlying. You don't necessarily see that in that format, but that's how it's represented for the 4 terms of the year. We have department and number and course description. Think, for example, this class here. Given student, course number, whatever our CRN is, department is CIS, number is 175. Course description is introductory SQL. Term can be whatever term it is. And my grade is A+. These are the fields directly analogous to the ones in the course that you're taking now. That's what they're supposed to represent. The combination of department and number, I can tell you, will determine the course description. CIS 175 has a given course description. CIS 176 has a different course description. Math 175 has a different course description, but the unique combination of these two does determine the course description. And there could be more than one section of the same course being taught in the same term. That does happen. So put some thought into this one. It's more of a thought experiment. And put your final solution at the bottom here. That is all you need to know and all you need to do for lab number 9.